Hello, this is Atif, and I welcome you to Base 2's FastAPI AsyncIO Foundation course. This is the first video in this series, and we will spend some time understanding AsyncIO, which is the backbone of FastAPI. If you want to take full advantage of FastAPI's capabilities, it's super important to understand AsyncIO. Beware that FastAPI doesn't enforce async. It is flexible and lets you write synchronous code as well. However, FastAPI's true strength is in async, the asynchronous programming. And the people who come from the synchronous programming background, for example, Django and Flask developers, it's not uncommon to treat FastAPI the same way, the synchronous way that they are used to it. And to be honest, async programs are a little trickier than the synchronous ones, but that a little extra effort pays you off in the form of scalability and better performance. Async IO is essentially an approach to multitasking. Traditionally, we know two approaches to multitasking: multiprocessing and multithreading. So, why another approach? Why async IO? Well, the answer is in the name. IO means input and output. Async IO is designed for the input-output bound tasks, or IO bound tasks. Some of the examples of IO bound tasks are reading from a file, writing to a file, database reads and writes, network operations like fetching data from an API. The second part of the name is async. In fact, the first part, async means non-blocking or non-sequential. While a process waits for an IO to complete, other processes may continue, as opposed to synchronous programming, which executes tasks sequentially. And the next task is blocked until the first one finishes. As said, async IO is designed to concurrently execute IO bound tasks, and this is where it shines. The traditional approaches, multiprocessing and multithreading, are designed for CPU bound tasks, and the CPU bound tasks are not really a fit for async IO. Okay, we will discuss this more in a bit, but let's see what happened that led us to the need of async IO. The World Wide Web, WWW, has a pretty long history since its coming into being in 1991. This history is full of developments and innovations. For the sake of our discussion, I divide it into two eras, pre-2010 and post-2010. Prior to 2010, most of the web apps used simple architecture design based on typical request response cycle, the HTTP request response cycle. The networks and devices were not as fast as we have now. Smartphones just started getting introduced. They were still evolving. First iPhone was introduced in 2007, and first Android phone was introduced in 2008. The users at that time were also not too demanding. They were much content and patient. They were okay with the page load times of a few seconds. That was expected anyway, given the limitation of infrastructure at that time. The developments after 2010 were quite dramatic. The smartphones and tablets became popular. Every hand has a smartphone now, which means the user on the web, the number of users on the web increased dramatically. The increased number of concurrent users meant an increased load on the web servers and web applications. IoT, WebSockets, streaming, and data-driven apps, they all contributed to the increased load on the web servers and web applications. And the users now also have a higher performance expectation. A page load time is expected to be within a second or maximum a couple of seconds. In many scenarios, users expect real-time notifications and real-time information updates without having to reload the page again and again, which was common in past. As a result of these advancements over the time, the web development also adopted to the new requirements. Post 2010, we see the single page applications and progressive web applications got trending. CDNs are more commonly used to serve static content for improved performance. Same way, edge computing and edge caching became a common design choice to reduce the latency. Microservices and event-driven design has been helpful in developing scalable and highly available systems. And to handle all that increased load of network traffic, heavy data reads and writes to and from the file storage or the database systems, to handle all this increased amount of I/O, asynchronous programming has been widely adopted in the various web languages and web frameworks. FastAPI is a very good example of such frameworks. Now let's take a look at multitasking possibilities in Python. Prior to Python 3.4, Python supported multiprocessing through its multiprocessing library and multithreading through its threading library. And in Python 3.4 in 2014, support for asynchronous programming was announced with the addition of AsyncIO library. Let's take a high-level overview of how multiprocessing and multithreading work and how AsyncIO is different. First, multiprocessing. As you can see in this diagram, operating system has a major role in controlling the parallel execution of tasks. OS schedules the tasks with the help of its component called scheduler. The OS scheduler preempts and evenly distributes CPU time among multiple parallel tasks. It is called preemptive multitasking. Let's say we have 3 CPU cores available and we have to run 3 processes in parallel. OS scheduler will assign one process to one core each. This is true parallelism, and the tasks are performed in parallel by leveraging the power of each CPU core. In the context of Python multiprocessing, a process consists of an instance of Python interpreter, the program that defines the tasks, and every process is assigned a separate memory block, which is not shared with other processes. You can see in the diagram that processes 1, 2, and 3, they have independent memory, which means that multiprocessing is particularly a resource-heavy approach, and it is suitable for CPU-bound tasks. For example, image manipulation, training ML models, etc. There are some details to multiprocessing, but in the context of our course, this level of understanding with multiprocessing is enough. Now let's take a high-level overview of multithreading. Again, as you can see in the diagram, threading is also a preemptive approach. Operating systems scheduler controls the scheduling of the tasks, which are threads in this context. Compared to multiprocessing, threading is a resource-friendly approach. As you can see, there is just one process, and the threads belong to the same process. This means that the threads share the same block of memory. A process is an instance of the application, while the threads are generally independent functions that can be executed independent of other threads running in parallel. Python's most used interpreter, CPython, has a different approach to multithreading due to its memory management implementation, which is not thread safe. Due to this limitation of not being thread safe, CPython has a global interpreter lock, that a thread acquires when it switches to the running state. And it releases the lock, that is the GIL, when it completes or goes on to waiting state or suspended state, in which case the next thread holds the GIL, the global interpreter lock, and it continues so on for the other threads. All of this involves quick context switches, which are generally so fast that the user cannot realize it. This is called concurrent execution, which is not true parallel execution. Looking at the diagram, you can clearly find out that not all the available CPU cores are utilized in Python's multithreading. This doesn't mean that Core 2 and Core 3 will never be used, but it just means that they are not utilized by multi-threading at the same time. This makes multi-threading in Python unsuitable for CPU-bound tasks. Prior to AsyncIO, multi-threading was the go-to option for IO-bound tasks in Python. All right, there are many important concepts related to multi-threading and multiprocessing that you should learn if you want to implement any of those. However, it is out of the scope of this course. Having said that, it's time to understand how AsyncIO works in Python. Looking at the diagram, you can say straight away that it's significantly different from multiprocessing and multithreading. Whereas the former, both approaches are preemptive, AsyncIO is a cooperative multitasking approach. OS does not control the task scheduling in AsyncIO. This gives more control to the Python program over concurrent execution of the tasks. Let's talk about a few terminologies related to AsyncIO. An event loop is the core and central figure when we talk about AsyncIO. The event loop is essentially a control structure, a loop looking for the events to occur. And this loop runs in a single thread. So it's a very resource friendly approach. The tasks are called coroutines in AsyncIO context. There is a ready task queue, as the name suggests. It holds the tasks or the coroutines that are ready to be executed, or they are in ready state. As an event occurs, for example, a task is scheduled to be executed every 5 seconds, the corresponding coroutine gets added to the ready tasks queue. The event loop picks the tasks from ready queue in FIFO order, first in, first out order, and hands control over to the first task it picks from the queue. Now, what happens? Well, the coroutine executes, and it either reaches its end to finish the execution, or it hits a point where it must wait for an I/O operation, such as fetching data from an API. In both of the cases, the coroutine yields the control back to the event loop voluntarily. The event loop immediately hands over the control to the next coroutine from ready queue. The coroutine executes and yields the control back to the event loop again, either as it completes the execution or as it awaits an I/O operation, maybe a DB write this time. This voluntarily yield of control by coroutines is what makes AsyncIO a cooperative multitasking approach. Good enough. Let's do a quick recap. AsyncIO is suitable for I/O bound tasks. Some examples are database reads and writes, file reads and writes, and network operations like posting data to a server or fetching data or content from a CDN. Event loop is the core of AsyncIO. It is a loop running in a single thread, generally the main thread, and it waits constantly for I/O events to occur. As the events occur, event loop adds corresponding tasks or the coroutines to the ready task queue. The coroutines are processed in FIFO order, first in, first out order. The coroutines execute and yield the control back to event loop voluntarily, and this nature makes AsyncIO cooperative multitasking. Normally, the coroutines are lightweight functions, and event loop is able to run thousands of coroutines concurrently. You might ask, what if the functions are not lightweight? This means that we are doing something wrong. This means that they are not I/O bound coroutines, rather they are CPU bound. And in such case, async I/O is not the correct choice. One last thing, event loop constantly waits for the events, and it adds corresponding coroutines to the ready queue. Which events does it look for? First type of events are I/O events, such as maybe a socket is now ready to read or write, a file descriptor has data available, or a subprocess has output ready, or server got a new connection. The second type of events are timer events, such as an API client waiting to retry a failed request in 3 seconds, a background task which is scheduled to run every 10 seconds. And the third type of events are callbacks, such as a file upload finishes and you must notify the user. All right, now that we have good understanding about three multitasking approaches, let's address the main question. Why is FastAPI built upon AsyncIO? FastAPI is a web framework, and it has been built to best suit the nature of web servers. Most obvious of the web server's job is to serve the web pages and web apps. While doing so, they are fully engaged in network I/O. In the meanwhile, they might also be writing data to a database or looking up for the data based on a user's query. Now they are performing database I/O operations. And when a user uploads a file, or when the server has to serve static files from disk storage, it is file I/O. The web servers find themselves dealing with the I/O bound tasks most of the time. Now let's do a comparison of the three multitasking approaches to find the answer to our question. Multiprocessing is suitable for CPU-bound tasks. It is a resource-heavy approach, so it can be ruled out for the lightweight I/O-bound tasks, being an overkill of resources. On the other hand, multithreading with the GIL had been considered an option for I/O-bound tasks before async I/O was introduced in Python. But it can't be used to achieve the high concurrency and scalability needs of web servers today. Why? Because it requires to span several threads, which gets limited by the number of available CPU cores. This also means that multithreading becomes significantly resource expensive. Lastly, async I/O. Async I/O's event loop runs in a single thread, which means it is really a resource-friendly approach. With cooperative concurrency, it can run thousands and even tens of thousands of concurrent tasks with the single thread. So async I/O is ideal for I/O bound tasks like a web server has to perform most of the time. Due to these advantages, FastAPI has been built on async I/O. The existence of FastAPI became possible only after async I/O was introduced in Python. We will build up from here, and in the next session, we will start the hands-on practice with Python's AsyncIO module. Stay tuned for the next video in Base 2's FastAPI AsyncIO Foundation course.